Hello again. This is Math 1120 coming to you from the College of DuPage. And the title of this lecture is Velocity and Acceleration in a Plane. As always, please be an active learner as you watch this video. To describe the motion of an object in a plane, we first need to be able to describe the object's position. And in this chapter, rather than as in the previous one, we're not just doing motion on a line, so we're doing motion on a plane. So what we will have is, we will have position is going to have an x coordinate and a y coordinate. And in fact, the position is going to be described as by a vector going from 0, 0 up to the point xy. So that is the point where we're sitting. And so you see, this is going to be we're going to be doing vectors. And so the magnitude of a vector is going to be the square root of x squared plus y squared, again the x component and the y component. This is what we worked on in chapter 1 with the vectors so much. So given that, then, if we have the vector r representing the position, then the average velocity of a particle in displacement delta, the vector r, is defined on the interval delta t. So the average velocity is going to be the difference between these two vectors, which in itself is going to be a vector. So the average velocity vector is going to be the change in the position vector divided by the change in t. So if the object is moving in the xy plane, then that has both an x and a y component. If it's only moving in one direction, the other component is 0. So let's do an example here then of motion in a plane. Suppose you're operating a radio-controlled model car on a vacant tennis course, so it is a flat surface. The surface of the court represents the xy plane, and you place the origin at your own location. And at time t1 equal 2 seconds, the car has x and y coordinates 4, 2. And at time t2, which is 2.5 seconds, it has coordinates 7 and 6. So you see it's moved. So for the interval from t1 to t2, that is from 2 seconds to 2.5 seconds, find the components of the average velocity of the car and the magnitude and direction of the average velocity. I hope you know what to do. Let's see how you did. Okay, talking about the solution, then we start here and we move up to this point. And so for part A, we want to find the components of the average velocity. So here we say, well, how much did you change in the x direction? Well, you changed 3 units in the x direction divided by delta t, which was 1/2 of a second. You do the arithmetic and you get this is 6 meters per second, and that is in the x direction. Now in the y direction, that's the change in y, you go from 2 to 6, which is 4, and that is over a 1/2 second, so that is 8. So you're moving 6 in the x direction and 8 in the y direction. So those are the components, but now we need to find the magnitude and direction of the velocity. So to find the magnitude, we're going to take the 6 and the 8, and we're going to use the Pythagorean theorem to find the length of this. So the magnitude is going to be the square root of 6 squared plus 8 squared, and when I take the square root, I get 10. And then I want to know what is the angle of the velocity. So that's going to be the inverse tangent of the y over x velocities. And that's going to be the inverse tangent of 8 over 6, or 4 over 3. And we get that that is 53 degrees. Let's look at another example. Consider now 2 toy cars that are initially at rest. The cars begin to move at time t equal to 0. And car 1 moves along the x-axis, and car 2 moves along a line that makes an angle of 45 degrees with respect to the positive x-axis. You need to draw this picture to think about it. As they move, the x1 component of car 1's position is always equal to the x2 component of car 2's position. Which of the following statements is true regarding the average speed, that's not the vector, and velocity of the two cars? The average velocities of the two cars are the same. Only the x components of the average velocities of the two cars are the same. Or C, the average speeds of the two cars are the same. You know what to do. Let's see how you did. Well, the answer cannot be A because the cars are moving in different directions, so the velocities can't be the same. C also cannot be correct because car 2 moves at a 45-degree angle, and the components of its average velocity in the x and y directions must be the same because it's a 45, 45, 90 right triangle. Its speeds, which is the magnitude of the average velocity, is therefore the square root of those things squared, which is going to be, since they're both the same, it's going to be 2, the average velocity of a sub x when I take the square root. So, and that this v average in the x direction should be outside of the square root. That's a typo. So car 2 is moving with a speed that's square root 2 times larger. So the correct answer has to be B. We also have a vector quantity for the average acceleration. So the average acceleration as a vector quantity is the change in the vectors for the velocity divided by the change in time. The units are going to be meters per square second. And even if a particle is moving at constant speed, it can have a non-zero average acceleration if the particle changes direction during its motion. Here's an application. Can you spot the 3 accelerators in this picture? You know what to do. Think about it. Let's see how you did. Well, there are 3 accelerators. One is this thing that can make you go faster. The brake can make you slow down. So those are both accelerators. But also, even if you're going at a constant speed, if you turn, you're changing the direction of the velocity, which is also an acceleration. Now that is a circular acceleration, and we're not really going to talk about that much, but for completeness, we're talking about it now. So the steering wheel, the brake, and the accelerator. Now let's look again at the radio controlled model of our earlier example. So suppose at T1, the car has a component of velocity 1 and 3. 1 in the x direction and 3 in the y direction. And at T2, which is 2.5 seconds, the components are 4 and 3. We want to find the components of the average acceleration and the magnitude and direction of the average acceleration during this interval. You know what to do. Let's see how you did. Okay, well, to find the components of the average acceleration, we need the components of the changes in velocity. Delta x and delta y, and the time interval, which is 1/2 of a second. So the change in the x direction is 4 minus 1 is 3. So the x component of the average acceleration is, after you divide by this, is going to be the 3 divided by 0.5 is going to be the 6. And the change in the y direction is actually going to be 0 because it stayed at 3. There was no acceleration. So there's only an x component, and that means it's just strictly 6 meters per second squared in the x direction. Here's another conceptual problem. A visitor to a picnic. An ant crawls at a constant speed on top of a square blanket you've laid out for a picnic. You've picked a flat horizontal lawn for your picnic and oriented the blanket rather, so that one side of it runs north and south and the other side runs east and west. The ant crawls onto the blanket at the northeast corner, traveling due west, and 60 seconds later, the ant crawls off the blanket at the southwest corner, traveling due south. In which direction does the average velocity of the ant point for the 60 seconds while it's on the blanket? You know what to do. Let's see how you did. The key idea is that the average velocity of the ant will point in the same direction as its displacement. Regardless of how the ant moves during the 60 seconds, its displacement during the interval points from the northeast corner of the blanket, its initial position, to the southwest corner of the blanket, its final condition. Therefore, the ant's displacement points in a southwest direction, so the average velocity must point to southwest as Burrell. The answer then would be C. In which direction does the average acceleration of the ant for the 60 seconds point while it's on the blanket? You know what to do. Let's see how you did. Even though the ant travels at a constant speed across the blanket, the direction changes. So there must be an average acceleration over the 60-second interval. The average acceleration will point in the same direction as a change in the ant's velocity, which is delta v2, which is delta v, the vector, which is the magnitude of the vector v2 minus the vector v1. So this delta v is the vector sum of a vector that points south and a vector that points east. So it is going to be southeast. In closing, now more than ever, time is precious. Each day must count. Do the math, it will make you strong. And now more than ever, take care of yourself and of each other.